We're starting our review now in the trig section. So we want to look at our basic graphs here first. So remember that we're getting values from the unit circle. So the sine starts at the y coordinate of 0. At pi over 2 on the unit circle, the sine is up at a height of 1. At pi, sine is back to 0. At 3/2 pi on the unit circle, sine is down at -1. And at 2 pi, sine is back to 0. So our sine wave, the first cycle around the unit circle, looks like this graph. And you want to make sure every time you do a trig graph that you've divided your first cycle into 4 quadrants. So it takes 5 endpoints to divide it up into those 4 quadrants. Cosecant, by definition, is 1 over sine. So the reciprocal of these very tiny numbers, like this value right here, the reciprocal of a very small number is huge. The problem is, what's the reciprocal of 0? It is undefined. So to graph cosecant of x, everywhere where sine is equal to 0, we will get a vertical asymptote because the reciprocal of 0 does not exist. So we could label these equations x equals 0, x equals pi, x equals 2 pi. The places where the sine coordinate is 0, cosecant is undefined. And then when we do the reciprocal of this value, which is 1, the reciprocal of 1 is 1. The reciprocal of these very tiny numbers gets very huge. So we're used to this idea of this curve flips over to go to positive infinity. And here, negative numbers that are small negatives go to negative infinity. And of course, this is just the first cycle. The cosecant graph would continue repeatedly, as would the sine graph. All right, our cosine graph, let's think of the unit circle again. So I'm looking here, at 0, cosine is 1. At pi over 2, cosine is 0. At pi, cosine is -1. And at 3/2 pi, cosine, oops, what did I do here? Cosine is back to 0. And I'm just going to scroll for more space. And when we're back to 2 pi, cosine is back up at +1. So make sure you don't draw this as a V shape. Remember, it's the same shape graph as our sine wave. So make sure you try to get curves in there. So let's label 0, pi over 2, pi, 3/2 pi, and 2 pi is where our cycle finishes. This height is at 1. This is at -1. And then we want to graph secant. Secant, likewise, same as we did for cosecant. Secant is the reciprocal of cosine. So wherever cosine is 0, secant is undefined. So we would flip over, and notice what I did here to go backwards to -pi over 2 so that we had a complete graph, so we don't have just 2 separate pieces. So you might, when you draw this, show a different so here would be our next vertical asymptote. So equations of the asymptotes here, x equals -pi over 2, x equals +pi over 2, x equals 3/2 pi, and so on, continuing infinitely. Our graph for tangent. Again, let's think about getting points from the unit circle. Remember, in the unit circle, the definition of tangent is y over x. So tangent is undefined whenever the denominator is 0. So where is the x coordinate 0? That would be at pi over 2 and 3/2 pi. So our asymptotes for tangent, -pi over 2, +pi over 2, 3/2 pi, and of course they would continue. Where is tangent equal to 0? That would be when the numerator is equal to 0. So y over x is the definition of tangent. So when is tangent equal to 0? When the y coordinate is 0. So that would be at 0, pi, 2 pi, and so on. So let's get our axis labeled here. And then how do we know about the rest of the shape of the graph? Well, let's think about tangent when we're in the first quadrant. We know that the tangent of pi over 4 is 1. And we know that the tangent, when we get to this place, the y coordinate is getting very large in comparison to the x coordinate. So do you see how the point right next to this point, the y coordinate is very large and the x coordinate is very small? So we know in quadrant 1 that the graph is positive. So this is at pi over 4 that we get a value of 1. And likewise, if we went backwards through quadrant 4, we know we would get negative 1 here at negative pi over 4. So we can repeat that pattern for a tangent curve. So in quadrant 1, between 0 and pi over 2, we know that every graph is positive. So for cotangent, if we think of the unit circle, cotangent is x over y. So cotangent is undefined when the y coordinate is equal to 0. And that happens at 0 and pi, and 2 pi, and 3 pi, and so on. So at 0, pi, 2 pi, we could go backwards here, negative pi. You only have to get one complete cycle labeled here, and that would be okay. And what happens at pi over 2? At pi over 2, the x coordinate is 0, so we would get 0 over 1. So at pi over 2, we get a value of 0. At pi over 4, tangent is equal to 1, so is cotangent equal to 1 at pi over 4. So our cotangent curve goes up again. We're in quadrant 1 here. In quadrant 1, every one of the 6 ratios is positive. So that's an easy way to remember the shape of our tangent graph. And this would be at 3/2 pi. And this would be at negative 1/2 pi. All right, so again, you don't have to do 3 of those graphs. 1 or 2 of them would be plenty. All right, let me pause a minute and fix the problems here. Okay, here we're going to graph inverse trig functions. So remember, the key for restricting the domain is that it has to be a 1-to-1 section. So if we think about our sine wave, notice that our sine wave would fail the horizontal line test. So how can we restrict it? We restrict it from a minimum to a maximum. So we're going to restrict it from negative pi over 2 to positive pi over 2. So if we're going to think about, remember what inverse functions do, they fold across this 45-degree line. So the inverse sine function looks like this. And we think about what we had on the sine function. This point was at pi over 2 comma 1. So on its inverse function, this would be at 1 comma pi over 2. So you can either label the coordinates on the axes, or you can label the coordinates at the points. So again, let's look at this red graph. This point down here in red, if I can switch pens, this point was at negative pi over 2, negative 1. So on an inverse function, the x's and the y's trade places. So this is at negative 1 comma negative pi over 2. And of course the 0, 0 point, when you reverse it, is still 0, 0. So this blue graph, so the blue graph is inverse sine. All right, let's do the same thing. Let's look at the graph of cosine. So a dotted function here is what the graph of cosine looks like. And again, it's not 1-to-1. It would fail the horizontal line test. So we would limit it from a minimum to a maximum. So we don't want to go over any hills or valleys, and this looks like we would go from 0 to pi to get a 1-to-1 section where there's no x's repeated and no y's repeated. So what happens if we fold this across the 45-degree line? Let's see if we can make this look like an accurate reflection. So I want to get a little curve in there. So let's see why I drew it this way. Let's look at some points on the red graph. On the red graph here we had 0, 1. So on the inverse function we would have 1, 0. On the red graph we have the point pi, -1. So on our purple graph we have the point -1 pi. Again, you can label them on the axes or you can label them next to the points. There's one more you should catch. This is at pi over 2, 0. So its reflection image right here is at 0, pi over 2. And the reason students sometimes have trouble with this is that they think pi over 2 is smaller than 1. Remember, to get your graph squared up, pi over 2 is about 1.57. So remember that your 1 has to be lower than your pi over 2 mark. Okay, how about inverse tangent? Well, first let's look at the graph of tangent. Hopefully you'll remember these quickly. The graph of tangent had its asymptotes at negative pi over 2 and positive pi over 2. Those vertical lines are x equals that value, and the tangent rose in quadrant 1. So there's the graph of tangent. Now if we fold this across the 45-degree line, think what happens when we fold. These points are going to flip, the x's and y's, and now instead of having vertical asymptotes, we now have horizontal asymptotes. So this equation would be y equals pi over 2, and this equation y equals negative pi over 2. And our 0, 0 point stayed fixed, and that would probably be enough for you to label the inverse tangent function. All right, looking at the time here, I think I'm going to stop this video and then come back and pick up with question 39 in our next video.